Okay, 12.4 is about vapor pressure, boiling point, and the Clausius-Clapeyron equation. This will be a big one. Now every substance that's a liquid or a solid is going to have a vapor pressure, meaning that it will vaporize to some extent until it reaches equilibrium with the gas phase at that pressure. So let me show you a figure that explains why this is. If we look at figure 12.19, we can see how different molecules within a substance are going to be traveling at different velocities. In a liquid or in a solid, they'll have different amounts of kinetic energy. The average kinetic energy depends on temperature, but the actual distribution of kinetic energy between the individual molecules is going to follow a curve that looks a little bit like this. And so here, if you have a substance with a temperature of 300 Kelvin, there's going to be a majority of the molecules that have not very much kinetic energy at all, but there is going to be some small fraction of the molecules that have really a large amount of kinetic energy. And some of them will have enough kinetic energy to break away from that liquid or solid phase and escape into the vapor phase. And so we call that the escape energy, and different substances might have a different escape energy. So if we compare bromine to water, remember bromine has only dispersion forces, and so it has relatively weak intermolecular forces, and so the escape energy required for a bromine molecule to break free into the vapor phase is relatively low. Water has hydrogen bonds, and so it has a very high escape energy. A lot of energy is required for water to break. In both the case of bromine and water, however, there will be at least some molecules that are traveling fast enough to escape. And so we see here the difference in escape energy explains why bromine would have a higher vapor pressure than water, because it has the weaker intermolecular forces. Vapor pressure is also dependent on temperature. So if we compare the blue curve at 300 Kelvin to the red curve at 320 Kelvin, this red curve has a higher proportion of its molecules here at the high kinetic energy end of the graph. And so for both bromine and water, a higher temperature will lead to a higher vapor pressure. And so you can take something with relatively low vapor pressure, and as you warm it up, its vapor pressure might become substantial. Oops. Sorry, there's another figure that I wanted to show you. There it is. It's pretty far along. Another way to think about vapor pressure is that, like we've talked about, the liquid molecules will have some small fraction of them that are capable of escaping into the gas phase. But then also gas phase molecules are going to have some small fraction of them that are traveling slowly enough that when they encounter the surface of the liquid, they will become stuck and they will recondense onto the liquid. And so vapor pressure is the pressure at which those two processes, the molecules escaping the liquid into the vapor and the molecules depositing from the vapor into the liquid, the vapor pressure is the pressure at which those two are in a dynamic equilibrium. So if we look at the last figure here, you can see that for every 3 molecules that escape, there will be 3 new molecules captured. And so that system has reached a steady equilibrium. And that is how we define the vapor pressure. Now if you have like an open room, where where a molecule that escapes the liquid has so much volume that it just never comes back, then you'll never be able to achieve the vapor pressure. Equilibrium will never be established, and the entire liquid will evaporate away. That is why you can take your wet clothes and hang them outside on a clothesline, and they will dry off even though they never reach the boiling temperature of 100 degrees Celsius. They'll still dry off, and that is because even below boiling, water has a certain vapor pressure. And as long as you're outside where the humidity is low and there's plenty of air to carry those water molecules away, well then they'll just they'll evaporate one at a time until your clothes are dry. Okay, let me go back here a little bit. Okay, most solid substances are going to have vanishingly small vapor pressures, like metal, wood, plastic. These have vapor pressures that are so small that they might as well be zero. And they are called non-volatile substances. So I'll write that down. Oops. Volatile. Okay, so to a chemist, volatile means that it has a substantial vapor pressure. Things like acetone, gasoline, these things, when you spill them, they dry up before your very eyes because they have a very high vapor pressure. They are volatile. Non-volatile substances have little or no vapor pressure, things like plastic, mineral oil or vegetable oil. And even water. You know, here in Utah, the air is so dry that things do dry out quickly, and so it's tempting to label water as a volatile substance. But most places it's more humid, and you know, compared to acetone and gasoline anyway, water doesn't dry up quite that quickly. So I guess water's at a good boundary between volatile and non-volatile substances. So here we see the enthalpy of vaporization for a number of different substances at different points. Sorry, I forgot the slideshow was up. We didn't need this figure here earlier, but we need it now. You'll notice that they each have a different boiling point. For water, the boiling point is 100 degrees Celsius. That's probably pretty familiar to you. But other substances have other boiling points. Something like acetone has a boiling point at just 56 degrees Celsius. So why is that? And what is the definition of boiling? Well, boiling is really the point at which the vapor pressure matches the atmospheric pressure. And so if water reaches the point where its vapor pressure is 1 atmosphere, then it's producing enough water vapor at a high enough pressure to kind of push the rest of the atmosphere away. And that's why it's able to produce bubbles. The bubbles are water vapor that is pushing out and making room for itself because it's at a high enough pressure to oppose the atmosphere around it. And so the boiling point, we talked about in the last section how that's the point where the temperature gets pinned, and any more energy that you add to it is going to go to a phase transition instead of changing the temperature. You can't get water higher than 100 degrees Celsius under standard atmospheric conditions. And these have different boiling points because they have different volatilities. Water has a relatively low vapor pressure, and so you need to heat it up a lot in order to reach that boiling point. Acetone, which has a much higher vapor pressure because of its weaker intermolecular forces, is able to boil at just 56 degrees. So as you warm acetone up, once you hit 56 degrees, then its vapor pressure is equal to 1 atmosphere of pressure, and it will begin to boil. And so each substance has a different boiling point, and technically the enthalpy of vaporization is different depending on what temperature you're at. That's ultimately because of the different specific heats of the liquid and gas phases. And you'll explore that in a little bit more detail if you go on to take Chemistry 3610. But for now, you just need to know that that makes it a little bit difficult to know what value to include in a table. So most of the time, I suppose you're going to be undergoing a phase transition at the boiling temperature. And so you see here we have enthalpies of vaporization for each of these substances at their own boiling point. But now these values are all dependent, representing different temperatures. And so it's also sometimes useful to give the enthalpy of vaporization at a standard temperature at 25 degrees Celsius. Now in reality, if you look at these numbers, the change in the enthalpy of vaporization is not terribly strong, and so it's less than a 10% change in most cases here. And so we're just going to use enthalpy of vaporization from here on out without even regularly making reference to whether it's at the boiling point or at the 25 degrees Celsius. Most numbers are going to be at the boiling point, just so you know, but we won't be drawing attention to that. Now, we can use the temperature dependence of the vapor pressure and the enthalpy of vaporization together in a really great equation called the Clausius-Clapeyron equation. So let me write that down. And I'll show you two different forms of the Clausius-Clapeyron equation, and then we'll show you how to use it. Okay, so the Clausius-Clapeyron equation relates the enthalpy of vaporization to the vapor pressure at two different temperatures. And there are two different forms of it. They're consistent with each other, but they're useful each at different times. So one of them says that the natural log of the vaporization of the vapor pressure, sorry, that's a pressure, let me make it a capital P. The natural log of the vapor pressure is equal to negative delta H of vaporization over R times 1 over T plus the natural log of beta. I'll just throw up the other form, and then we'll talk about some of the figures in here. So the other form says that the natural log of P2 over P1 is equal to delta H vaporization over R times 1 over T1 minus 1 over T2. And so these are two different forms of the same equation. this form up here is if you have a whole series of data across lots of temperature ranges, then this is the form of the equation that you would use to find a best linear fit to your collection of data. We won't really be using it very much. Instead, because we need to give you simple problems in order to have you solve them without using a spreadsheet or a fancy calculator. Instead, we have this form, which is designed to reference only 2 points of data. You'll have temperature 1 and pressure 1, so you'll measure the vapor pressure at a given temperature, and then you'll measure the vapor pressure at another given temperature, and from that you'll be able to calculate the enthalpy of vaporization. Or you could, if you know the enthalpy of vaporization, you could use this equation to predict the pressure at a different temperature. So this is the form that you'll use most often. So let's walk through it. First of all, this beta is a number that you'll notice falls away in this form of the equation. It's just an extra empirical factor that represents the intercept of the line with the y-axis when you put this on a graph. And so you don't really need to worry about the value of beta. We'll never ask you to calculate the value of beta. And then your temperatures here. Temperatures need to be in units of Kelvin. You cannot use degrees Celsius. You need to convert your temperatures into Kelvin. Your pressures can be in any unit you like as long as they are consistent with each other, because you divide one by the other. And then your enthalpy of vaporization is usually given in kilojoules per mole, but R here is going to be in units of 8.314 joules per mole Kelvin. And so just make sure you resolve that inconsistency one way or the other. The way I'll do it is I'll use 8.314 because that's a number that we're familiar with. That will give me an enthalpy of vaporization in joules, and then at the very end I'll divide it by 1,000 in order to get it into the conventional kilojoules per mole. Now this is the same R gas constant that you've used before, that sometimes has a value of 0.08206 liters atmospheres per mole Kelvin. Right? And these represent the same quantity, it's just a unit conversion. Just like I can say 12 inches and 1 foot are two very different numbers that represent the same quantity because they're in different units. This is the number that we'll use with the ideal gas law, PV equals nRT, but we do not want to use that here. For Clausius-Clapeyron equation, you use 8.314 joules per mole Kelvin. Okay, so let's put this into practice. Well, we're going to need a lot of board space, so I'm just going to kind of erase it all. And I'll rewrite this 2-point form of the Clausius-Clapeyron equation at the top. So the natural log of P2 over P1 is equal to the delta H of vaporization over R times 1 over T1 minus 1 over T2. Okay, and in the linear form of this equation, there was a negative in front of the enthalpy of vaporization. In this form, there is no negative. It comes down to whether you put P1 or P2 on top. But this is the way that your textbook writes the equation, so this is the one I want you to know. Make sure that you have P2 on top, P1 on bottom, and then T1 1 over T1 minus 1 over T2. And let me just really quickly, before we do a practice problem, I want to really emphasize that 1 over T1 minus 1 over T2. This is very much not equal to 1 over T1 minus T2. Okay, that is not allowed in math. And so you're going to have to go through this algebra without making a nice simplification like that. Okay, so here's a practice problem. So methanol has a normal boiling point of 64.60 degrees Celsius. So 64.60 degrees Celsius is the normal boiling point. And what that means is that the pressure at 64.60 degrees Celsius is equal to 1 atmosphere. That's what the boiling point means. The vapor pressure is equal to 1 atmosphere for methanol at 64.60 degrees Celsius. And it has an enthalpy of vaporization. Equal to 35.2 kilojoules per mole. And remember, we need to resolve our units here to have it match R, so I'll just immediately say that's 35,200 joules per mole. So the question is, what is the vapor pressure of methanol at 25 degrees Celsius? So let's look at what we have. We have a temperature 1, we've got 25 is temperature 2, we've got pressure 1, and then our unknown pressure is pressure 2, and we've got this enthalpy of vaporization. So let's put this into our equation. Natural log of P2, our unknown pressure, and 1.00 atmospheres is equal to our enthalpy of vaporization, 35,200 joules per mole, over R, the gas constant, that's 8.314 joules per mole Kelvin, all over 1 over T1. Now that's 64.6 degrees Celsius. We'll need to convert that into Kelvin by adding 273. So that will give us 337.6 Kelvin, right? 273 plus 64.6. I'm pretty sure that's correct. Minus 1 over T2, which is 25 degrees Celsius. That's 298 Kelvin. And that is our equation, which is a bit imposing, but you'll notice we just have one unknown right here. So we can take care of this one little bit at a time. I'm going to put up my calculator. And let's see, so let's start by figuring out this difference in the temperatures. So I'll say 1 divided by 337.6 minus 1 divided by 298. And that's going to be a negative 0.003936. Oh, 3 zeros. 0.003936. And that has units of inverse Kelvin. Okay, and now I'll take that number and I'll multiply it by my enthalpy of reaction and divide it by the gas constant. So we'll take that answer and we will multiply it by 35,200 and divide by 8.314. And what we get is that the natural log of P2 over 1 atmosphere is equal to a pretty easy number now, negative 1.6665. Negative 1.6665. Okay, now how do we deal with that natural log? The natural log is the inverse of exponentiation, and so exponentiation is the inverse of the natural log. In other words, we'll take e raised to the power of the natural log P2 over 1 atmosphere. And what that does is undoes the natural log. So we'll just now have P2 over 1 atmosphere is equal to e raised to the power of negative 1.6665. And if you have a graphing calculator, you'll want to make sure you can figure out where that that little e is on your calculator. So for my computer here, it's going to be a little bit funny, but that's what it'll look like. And yep. To be undoing the natural log. Okay, and I get 0.1889. So P2 over 1 atmosphere is equal to 0.189. 0.189. And right now that's a unitless quantity. All of the units here canceled each other out. Whenever you're taking natural logs or exponents, you should have a unitless quantity. But we'll go ahead and move this 1 atmosphere over to the other side. And we end up with a P2. This is just barely going to fit. P2 is equal to 0.189 atmospheres. So did that fit? Yes, just barely. Okay, so I know that's a rather intimidating sort of a problem, but we need to do another similar one where we're given the two temperatures and we're asked to find the enthalpy of vaporization. So let's erase this board and we'll start up again on it. Okay, so diethyl ether has a vapor pressure of 401 millimeters of mercury at 18 degrees Celsius. And it has a vapor pressure of 660 millimeters of mercury at 32 degrees Celsius. And so we can call this P1 and T1, P2 and T2, put them in the equation here and solve for delta H of vaporization. Let's really quickly convert these into Kelvin. 273 plus 18 degrees would be 291 Kelvin, and then 273 plus 32, is that 305 Kelvin? Okay, and we can put them into the equation now. The natural log of 660 millimeters of mercury over 401 millimeters of mercury is equal to our unknown delta H of vaporization. That's what we're solving for. Over 8.314 joules per mole Kelvin times 1 over, make sure I get this right, 291 Kelvin minus 1 over 305 Kelvin. Okay, so we've got pressure 1 and temperature 1, pressure 2 and temperature 2. And it's a bit tedious algebraically, but you can go ahead and use your calculator. You can probably solve it a bit more easily than me. I'm going to take the natural log of 660 divided by 401, and I'll go ahead and multiply that by 8.314, and I will divide it by, let's just do this in one go, divide it by that quantity, 1 divided by 291 minus 1 divided by 305. I believe I've put that all in properly, and I get a delta H vaporization equal to 26,263 joules per mole. And we can go ahead and convert that to kilojoules just by dividing by 1,000. So that'll be 26.3 kilojoules per mole when we consider we only get 3 sig figs. Okay, so that is the Clausius-Clapeyron equation. We've talked about normal boiling points. I guess not on this example. In our last example, we used a normal boiling point, and that was the boiling point for 1 atmosphere of pressure. If you have a lower atmospheric pressure, then you'll have a lower boiling point too, because boiling is when the vapor pressure equals the current atmospheric pressure. So here in Cedar City, our elevation is somewhat above sea level, and so our actual atmospheric pressure is like 0.82 atmospheres instead of 1 atmosphere. And that means that water will boil at less than 100 degrees Celsius. I forget what it is. It's like the low 90s. You know, it's about 5 or 6 degrees in boiling point reduction. And that is because of the low pressure here. You've probably also heard of a pressure cooker, and that's where you will boil food, but you'll seal the pot that you're boiling it in, and the water vapor will build up pressure inside that pot. And as the pressure increases, then so does the boiling point. And so a pressure cooker is able to take water above 100 degrees Celsius. And that is what allows you to cook food more rapidly in a pressure cooker than you could just boiling it on an open stove. Playing games with temperatures and pressures and things is able to allows you to take mixtures of substances and purify them through a process called distillation. Actually, let me pause a minute because I'm realizing I forgot to show you one figure that relates to the Clausius-Clapeyron equation. Okay, so this is how you might make the Clausius-Clapeyron equation into a linear format. If you were to take the pressure at a number of different temperatures and plot the natural log of the pressure as your y values and the inverse of the temperature as your x values, then you would get a line. And for like an analytical chemist, you always want to do your best to get your data to fit a line. Curves are not as reliable as far as interpolating points between them and finding useful constants like the slope and the intercept. So that's why the Clausius-Clapeyron equation has this form. The natural log of the vapor pressure is the y value in this equation, and then the inverse temperature is the x value, and that makes your negative delta H of vaporization over R equal to the slope of your line, and then the natural log of beta is just the y-intercept. So if you had a lot of data, you would want to take the inverse temperature and the natural log of the pressure for each data point and plot them in this way. But we're always going to give you only 2 points, and you'll notice the 2-point formula also has the natural log of the pressure and the inverse temperature. It's just written in this way to show the relationship between 2 individual points instead of a line that could accommodate a whole set of data. Okay. I also mentioned that at Cedar City, the boiling point of water is in the low 90s instead of at 100 degrees Celsius. Well, if you drop the pressure low enough, say using a vacuum pump and a sealed chamber, then you can actually drop the boiling point of water to be 25 degrees Celsius. So a decent vacuum pump can get down to 24 torr of pressure. When that happens, water will boil at room temperature. And that can make for some pretty cool demonstrations because as the water boils away, it can cool down, and if you get the pressure even lower than 24 torr, you can actually boil the water until it freezes, which is a bit of a mind-twisting idea. So here is distillation. Suppose you had a mixture of 2 different substances, and one of them is more volatile than the other. Then let's say you have a 50-50 mixture of water and ethanol in your flask. But ethanol has a higher vapor pressure than water. Well, then the vapor above your mixture is going to be enriched in the ethanol. Your 50-50 mixture of liquids will produce something like 60% ethanol and 40% water. And so in distillation, what you do is collect the water vapor, and you might encourage rapid production of the vapor by heating it over a burner. You collect the vapor, and then you recondense it to form a liquid with a new concentration that is enriched in the more volatile of the 2 substances. What's left behind in your original flask eventually will be enriched in water, and what you collect in the flask to the right will be enriched in ethanol. And if you like, you can then take that flask on the right and distill it as well. So you can do multiple repetitive distillation procedures. Each time you'll be enriching the composition of the more volatile substance. And so water and ethanol is, of course, a very practical example. People will distill ethanol all the time to produce liquors with a higher alcohol content than you can get just through brewing. And it's not just water-ethanol mixtures, but distillation is really important in fossil fuels. So what you actually pump out of the ground at an oil pump is a complex mixture of many different substances, and they all serve very, very different purposes in industry, and they're no good when they're all mixed together. And so a distillation column is an apparatus that sort of simplifies and expedites this idea of distilling one step after the other, after the other, after the other. And so you'll take your crude oil, you'll put it through this distillation column, and there are some other processing units that you see on the right, but ultimately you'll take that crude oil and you'll split it up into things like butane at the top and propane, gasoline in the middle, kerosene a little further down, diesel, and then lubricating oil, that would be like motor oil, and anyway, all the way down to the residues, which will be more like tar than like gasoline. And so you'll notice they all have different numbers of carbons to them. The vapors are things that have 4 carbons or even fewer. And the residues will have dozens and dozens of carbons. And their difference in melting points and boiling points is what allows this distillation column to separate them. And then they get sent to different places. The gasoline gets sent to the gas station, and the butane gets sent to be put in pressurized bottles, and the oil gets sent to the auto shop for motor oil changes, etc. Okay, we already covered the equilibrium. So anyway, that's distillation, and treating distillation rigorously and mathematically is really fun, but we will do that in a later course. So all you need to understand is the basic principle that different vapor pressures can allow you to purify a mixture such that the more volatile substance is enriched in the vapor phase and the less volatile substance is left behind and enriched in the liquid phase. That's the basic principle of distillation that you need to understand. Take 3610 if you want to do all sorts of math and look at lots of really great complicated charts about distillation.